instrumental, which is a manufacturing optimization platform focused on issue discovery, failure analysis, and quality monitoring. And I'm AWS machine learning hero and passionate about usage of cloud for AI and machine learning applications. And today I want to tell you about how to build scalable end-to-end deep learning applications in the cloud. So basically, I want to tell you how the usual data science project looks like. Then I want to cover different AWS services available for this task, and what are the main patterns when using them together. So just a bit of the introduction. Want to kind of cover what this talk will cover and won't. So I will try to kind of cover ways of running containers on AWS, workflows on AWS, and how to use them together. I won't be going into specific details for each individual service or no-code ML solutions. And basically, main highlights is how to use and utilize cloud workflows for your application, how you can choose your AWS services based on your application, because depending on the context, different services could be useful, and how serverless could be useful when building ML applications. OK, so first, let's take a look at why serverless even can be useful for machine learning project. So here's how the usual data science process looks like. So we start from business understanding, we collect data, build a model, deploy it, and get customer feedback. Let's see how it would work in real life. So let's say I want to build a model which will detect whether there is a corgi or not a corgi on the photo. So for the corgi, it will be corgi. For a cat, it will be not corgi. I took data set from my phone, so it has photos of my corgi. And I took pictures of some random cats from the internet. Next, I trained the model based on this data set. I productize it, build it in Docker container. Now it's part of ECS, build load balancer. On top of it, now I have like deep learning web server. So now I decided to run inference on some image. And it returns that it's a corgi. Even like we can see that it's just a German Shepherd. What happened wrong? Maybe the training data set wasn't good enough. It didn't have full data. Maybe model is not robust towards having unseen data. Maybe inference code has a bug. So at this point, we don't know for sure. So what it means is that basically we should be able to get this kind of feedback early and understand whether our deep learning model works or doesn't work in production. So that's why the whole approach to ML is being able to start really fast to get early feedback, have flexible infrastructure so that you can easily add more data, change some services, and so on, and be able to integrate with production so that you can get this real customer feedback. So in my case, I will probably use a more broad definition of serverless. Basically, here you can see different ways of deploying applications, starting from on-premise, where in blue, basically, you see what you control, and in transparent, what you don't control. And in my case, I will cover everything between container as a service to function as a service, effectively where you don't have to worry about provisioning specific machine or scaling them. Basically, on a very general level, we can say that it's on-demand cluster, worker, or service, which will scale by itself. No upfront costs, pay-as-you-go pricing, and no payment for idle time. Very low operational support, defined as infrastructure as code, and can be integrated with other services. So how does it help us with machine learning? Because it has low operational support and no upfront costs, it's very easy to start. Because it's defined in infrastructure as code and there are integrations, it's flexible. So if we want to add service or replace service or change configuration, it's very easy to do. And because it's scalable and has integrations, it can be integrated with real production. And you can start getting insights right away. So when you have to build real ML infrastructure, there are a lot of things where you need to make a choice. And there are although it's not, I would say, a binary, there is machine learning part, there is ML ops part, that basically if you only care about model architecture, it's machine learning. If you only care about business logic, then it's architecture, MLOps. It basically goes in different ways. Here, I want to cover different services and workflows, and so that you have enough information to make a decision for these parts. So when you design ML in production, there are usually 3 different tasks which you have to keep in mind: how to process data, how to train the model, and how to make inference. So with data preprocessing, the challenge is combining data from multiple sources, being able to process it in scalable way, and being able to combine different types of compute. With training, usually you just need to train the model like based on some set of hyperparameters, and the challenge here is that GPU instances are expensive, and it has high level of uncertainty. If you want to compare to normal software engineering, so you cannot fully automate the process. Sometimes you need some human making a decision. And for the inference, basically where we want to make predictions with our model, the challenge is effectively its production. So it has to adhere to production requirements: latency, load, cost, maybe handle multiple frameworks, business logic like model versioning, rolling out new models, and so on. So first, I want to start with covering serverless compute for machine learning. So in this case, it will be container as a service and function as a service. I will kind of look at it as a serverless cluster, we could say, where you just define code and launching configuration, and you don't care about how you scale the whole thing. At any point in time, you just don't need to care about how many machines there are, and so on. And here, depending on AWS service, you will have different scaling techniques. From AWS batch, which is effectively just scalable cluster based on job queue, to Lambda, which effectively just scalable worker with 0 idle time. If we put them like all the services together to compare them, we can basically have a spectrum here. So on the left, we have like managed cluster. It's just that we don't have to manage it. AWS manages it for us. Very customizable. You can use any type of instance, and it has the cheapest compute per second. On the other hand, we have pure function as a service. We have fully scalable, can start from 1 to 10,000 in seconds, 0 idle time. We never pay for what we don't use, and very fast init compared to managed cluster. So we have batch on the left, SageMaker jobs and Fargate in the middle, basically more working as perfect container as a service, where you define container, you have some idle time, but it's just container running your job, and so on. If we look more in depth and compare pricing, it kind of gives us insight like how these services are different. For the same type of compute, we basically see that Lambda is almost 3 times more expensive than batch, and if we compare to Spot, it's even more times more expensive. But if we look in depth how the pricing works, like with the batch, we will have a lot of idle time. With Lambda, 0. Same thing goes for GPU. Even though AWS batch for the same compute is cheaper than SageMaker, exactly same compute, because you don't get idle time with SageMaker, and you always get like 1 job, 1 instance, that can give you cost optimization. So if we put all of them together and like compare different pros and cons, we can see that Lambda is perfect for short-term processing. SageMaker, Fargate, like SageMaker is more focused on deep learning tasks which require GPU. Fargate can be used as container as a service for processing long-running CPU tasks. And batch has the highest customization, and if you need to use some custom instance and so on. So next part which I want to cover is, do you really need GPU for your task? Because like machine learning almost always connected to the notion of GPU. But for a lot of tasks, you don't like, and GPU really provides good speed. Like for training, it's almost always GPU. But let's say for inference, you will get the best speed with GPU. But when you deploy something to production, you also have to care about scalability and cost. And on that side, GPU is harder to scale. It takes more time to initialize, and it's more costly. So if, let's say, we compare different types of instances and Lambda, running the same inference of the same model, Inception Wave 3, used for image classification, we can see that basically, even though, let's say, Inference has the fastest inference time, and it has the lowest cost of 1 million predictions, it has the most expensive server. So you can see that you need to pay $200 per month. For C5 large, basically, even though like CPU instance is slower, you pay less. And if you compare with Lambda, for each of these type of servers, you still have to pay some money per month. So if you have less than 1 million predictions per month, effectively Lambda is the cheapest option, because you just don't have to pay for idle time. So next, I want to cover different ways of organizing compute. So let's say we decided about compute. Now we need to stitch them together. And the thing here is kind of how we can utilize modular approach. Let's say we have our training application to train model, and it uses some machine with GPU. But in reality, it doesn't use GPU for all the steps. It doesn't need it for data gathering or data preprocessing, only for model training. So effectively, we can try to minimize GPU idle time. And minimizing GPU idle time meaning that we try to put different parts of the processing task on different types of compute. But to make it work, we have to stitch them together to make it part of the same application. And here where we can get real value from cloud-native workflow services, where effectively nodes are different services which we can call, where we can have native support for functions as a service and containers as a service services which I mentioned before, which will scale based on your needs, and you can basically be very flexible when organizing logic for it. So here I would say it's kind of similar to the compute, where you can have hosted, managed Airflow, where you basically get customization level of Airflow just on AWS, and you can run it locally. And you have fully native solutions like step functions and SageMaker pipelines, where they are fully scalable, pay as you go, and have native integrations with other AWS services. So here, basically, SageMaker pipelines are very focused on deep learning applications, and very easy can be integrated with SageMaker services. The challenge is that sometimes they're not as integratable with other AWS services, though you can add Lambda, and that effectively means you can run anything. With Airflow, it's very easy to run locally, and basically with Airflow plugins, you effectively can do anything. But you don't have this like really nice native integration which you get with step functions. So now, kind of with covering this like compute and workflows, I want to start covering patterns which you can utilize when uniting these both together. So for these patterns, we'll utilize all the compute which I mentioned, because compute is really different, and step functions for organizing workflows. Step functions because they have integrations with all the services, native one, and they scale really good. And in our case, basically, we will use Batch and SageMaker for GPU jobs, Fargate for CPU jobs, long-running, and for Lambda for short-running CPU jobs. So let's start with data processing. So here it can be very simple. We just like download data in one case with one, let's say, Lambda. Then we use SageMaker to run this training job. And then in case we need to process something in parallel, so let's say we have 10,000 images, and we want to do some pre-processing for 10,000 images, that can be done in Lambda. But if you need to do something on the whole data set and you really need a lot of RAM, you can use a large machine on SageMaker. Same thing can be achieved with Batch or Fargate. The only difference is with SageMaker, you get a lot of things integrated for free, like mounting bucket and treating it as file system. Here, you will need to put your input data in a separate S3 bucket, download it on Batch Fargate, and put output data in a separate S3 bucket. Effectively the same thing. So where would it work better? So if you have peak loads, it will be able to scale. If you have complex custom logic, it will be also helpful. And if you need to unite different frameworks, different programming languages, and so on. For example, if you work with data lake. So where it wouldn't work? So if you need to run this data analysis synchronously, then AWS Lambda or cluster will be easier. If you have low CPU RAM consuming workflow and you really want to optimize costs, then SQS Kinesis plus Lambda will be a cheaper solution. Here's a link to the open source repo, which I contribute to. It has different types of patterns, which I will mention today, which have step functions, Lambda, and batch and Fargate. Everything is written in serverless framework notation. So it's basically one-line deployment. So it's very easy to start with. You don't need to figure out how to set up VPC for AWS batch or for Fargate. Everything will be already configured. And it's fully pay-as-you-go. So once you deploy it, 0 costs incurred per minute, unless you run some workflows. So next part is training. Here, basically, same thing with SageMaker. The main advantage of SageMaker that it will handle a lot of things for you, like hyperparameter optimization, handle model and input data, checkpoint handling, and even metrics gathering, and even distributed training. With batch, you effectively can get the same thing, you just need to implement it yourself. So you can just need to kind of provide this data, all parameters, checkpoints, and everything, and then you need to read it and do the whole thing. Another way is that you can integrate it with external infrastructure. Because GPU machines are costly, sometimes it's more efficient if you have on-prem GPU or, let's say, another cloud. And in this case, you can use step functions as a glue between your production infrastructure and some external GPU. In this case, basically, your step functions gets into the task state, and then you have a GPU machine which continuously makes requests to it. It finds the job, loads parameters and data from S3, trains the model, uploads it, and then the step functions handles the model productization and making sure that the model is published within your production infrastructure. So where it would work? So as always, with peak loads, or if you have rare training jobs, or if you have some complex logic, where you want to, for example, send some notifications or other parts like this, or you want to integrate external infrastructure with the cloud infrastructure. So where it wouldn't work. So if you have like very fast fine-tuning and you really need to have some real-time training jobs, there are cases like this. In this case, cluster would be more preferable. If you need to maximize training speed, also cluster, because it will have 0 startup time. So same repository, link, it has different serverless templates, so feel free to use them. It's completely MIT licensed and so on. And finally, inference. So for inference, I kind of want to step back and compare like serverless versus non-serverless way of doing it. So if we just want to use same inference using clusters, the standard thing, like you need to deploy a bunch of services like cluster, load balancers, and because you want to minimize cost, you need to use Spot, a load balancer group, and so on. With serverless, it becomes very straightforward. You just have API gateway and Lambda, and you achieve the same result. There is a catch, though. If you decide to use something like Lambda for inference, in addition to GPU versus CPU thing, which I mentioned before, because it will be CPU one, so it will be a bit slower, but more scalable, you will get another challenge, cold start. So this is the standard side about cold start. So when you run AWS Lambda, when you run it for the first time, it incurs some additional latencies. Some of them on AWS side, some of them on user side. So it needs to download the code, set up the container, initialize the code, and execute the code. So what it means in machine learning inference context is that basically it needs to load the libraries, download the model, initialize it, preprocess data, and run the inference. All these things all contribute to the cold start latency. And if you have to optimize your speed, you not only have to think about optimizing warm inference, which is usually the case when you work with inference, but optimizing something where usually people who work with machine learning don't care about. For example, what's the size of inference framework, or what's the, like, how do you package it? And here, basically, depending on your choice, for example, whether you use Docker image or zip file, you will have different init time on Lambda. Depending on which type of libraries you are using, it can affect it. So when you design inference in a serverless way, you basically have to make a lot of different decisions. For example, zip versus Docker image. Docker image compared to Python runtime will have almost 1 additional second. Model, do you store it with code, with zip and Docker, and increasing its size, or do you load it from S3 or EFS? What type of framework are you using? For example, if you're using TensorFlow or Torch, it means that it will wait a lot, and it will have additional latency just because you need to load the libraries. With TF-Lite or Pinvina or Onyx, just because they are lightweight, you will get additional performance boost. What is your configuration between CPU and RAM? Because sometimes you can do a lot of, like, it will make the inference more expensive, but at the same time, it can do it faster. And whether you will use standard x86 processor or Graviton 2. To show more specific benchmarks, here the same comparison, but with Inception V3 image classification model, different frameworks, different Lambda configurations. The most important part here is to kind of first, you need to make sure that, like, what's your timings for cold invocation and what's your timings for warm invocation, what's your cold cost and warm cost, and understand how it's affected, let's say, by CPU configuration. Because here you can see that even though, let's say, we have faster inference when we use more memory, the inference itself becomes more expensive. So balancing speed and cost here is about balancing CPU and RAM. Another example, here it's, I would say, more machine learning example, and comparison Graviton 2 versus x86 based Lambda. The same thing. Basically, whether you run your training machine learning model or inference sync on it, you will get different timings and different costs. And with Graviton 2, it can work better because Graviton 2 both cheaper and can work faster. But as always, you need to benchmark your workflow on both to have an understanding. Because maybe inference will be almost the same, but training will be different, and so on. So some life hacks for serverless inference. Basically, you want to make sure that your model is stored in memory so you don't reload it during warm invocations. EFS can work faster than S3 for loading the model, but it will have limited throughput. So in case you have peak loads, you may have additional latencies. One way to optimize it is not storing the full model and just part of it, and downloading model in parallel from S3. Something, I would say, performance boost you get if you get Lambda with multiple CPUs, you get to load things from S3 faster. On architecture side, you can effectively, if your model is pretty large, you can separate different layers on different Lambdas and chain them together. You can balance RAM and timeout to optimize your costs or optimize your speed. Depends on what your preference. And check if Graviton 2 Lambda works for your case faster and cheaper. So with serverless inference, there are different, I would say, tasks where it works. So it could be your pet project where you just don't want to pay anything, and within free tier you get zero cost. Maybe it's some simple MVP you need to do over day for your startup or project. just to show how it works in production. If you have a very simple model, then just having this architecture will reduce cost because it will fully scale to your demand, so you have zero idle time. And if you have peak loads and it's hard to scale clusters, that will also work. So where it wouldn't work? So if you really need to squeeze real-time response, then you need cluster. If you need a lot of data or processing power, you need cluster. Once you start hitting 10, 20 million requests or more, you can start thinking about cluster because it may be more cost efficient at this point. So link to another repo, Lambda Packs. It effectively has different packages ported for Lambda, some deep learning, machine learning ones, so you can start working with them right away. So to summarize, these cloud workflow services are best to end deep learning pipelines because it can work even if you're doing research. It can work if you just want to start and play it for your pet project because they don't incur costs unless you run them. And they can scale based on your demand. And different AWS services can be used depending on the context of your task. So you need to make a decision. So it's not like one size fits all. It always depends on your context. And these pipelines, which I mentioned, they doesn't have to be used by, like, if you're a large company. Like, you can really deploy it even if you're just like one-person company. So thank you very much for your time, and would be happy to answer your questions. Here are the links to all the repos, and my website has links to these slides. So basically, yeah, I will repeat the question. So basically, the question is how the Lambda scale is different from EC2. Basically, I would say EC2 will be part here of both batch and Fargate. Basically, it's just that it will scale EC2 instances for you. So Lambda has their own worker. Batch will effectively have EC2 managed by it, so it will manage cluster size for you. But you don't need to kind of worry about like how to scale this cluster. Batch completely manages it. Thank you very much for your time.